Today we're going to talk about invertibility and isomorphisms. First, let's review some concepts of the composition of linear transformations. Say that we have two well-defined maps, T and U, T going from V to W and U going from W to Z. Recall that the composition U circle T is that map that takes an element X from our domain V and sends it to U of T of X as an element of Z. Here you can see a diagram of how this works. On the left, we have, instead of V, a set A. In the middle, we have, instead of W, a set B. And on the right, we have C instead of Z. You can see here that the composition G circle F is like that of the composition U circle T. We start on the left and go all the way to the right. Let's say that V, W, and Z are three vector spaces over a common field F. First, the collection of all linear transformations, T going from V to W, forms a vector space. Second, if we have the composition of two linear transformations, then we have another linear transformation. Third, let's say that we have bases beta for V, gamma for W, and alpha for Z. Then we can consider the matrix representation of the composition U circle T. This will just correspond to the products of the matrix representations for U and for T. A diagram here will help explain what we mean by all of this. Notice that beta is contained in V as a basis, gamma is contained in W as a basis, and alpha is contained in Z as a basis. We can use our standard representations, namely phi sub beta, to take a vector and consider it as a linear combination of the elements from the bases. We can also map horizontally from left to right by considering our linear transformations T and U. Those will correspond to two matrices, which we'll denote as A and B. The point is, moving from the left-hand column to the right-hand column corresponds to a product of matrices. Recall that this script L of VW is defined as follows to turn it into a vector space. The elements of this set are just the linear transformations from V to W. By addition of two linear transformations, we'll define it as follows. Say that T1 and T2 are two linear transformations from V to W. We'll define T1 plus T2 as follows. It's that map that takes a vector X from the domain V and returns T1 of X plus T2 of X as an element of the codomain W. We can define a similar idea for scalar multiplication. Given a linear transformation T1 and a scalar C, we define C times T1 as that linear transformation as follows. It'll take a vector X from the domain V and return C times T1 of X as a vector in the codomain W. We can also define the product of two matrices as follows. Say that B is a P by M matrix. Here M is the number of columns of B. And let A be an M by N matrix. Here N is the number of rows of A. Then the matrix product, B times A, is that P by N matrix whose entries are defined as you see here on the screen. We'll give a few examples. The product of a 2 by 2 matrix and a two-dimensional vector is another two-dimensional vector, as you see here on your screen. More generally, the product of an M by N matrix and an n-dimensional vector is an m-dimensional vector, again as you see here on your screen. The product of two 2 by 2 matrices is another 2 by 2 matrix, as you see here on your screen. Let's use all of this to now introduce the concept of inverses and isomorphisms. We'll begin with the motivating result. Let's say that V and W are two vector spaces. The following three statements are equivalent for a linear transformation T going from V to W. First, there exists a unique function u, not necessarily a linear transformation, such that T circle u is the identity map on W, and similarly, u circle T is the identity map on V. Second, this map T is both one-to-one and onto. Third, the rank of T is equal to the dimension of V is equal to the dimension of W. Recall that the rank of T is the dimension of the range of T. For those following along in the textbook, you may wish to compare this result with the discussion in the appendix. Using this concept, any linear transformation T satisfying either of these three equivalent properties is said to be either invertible or an isomorphism. The function u that we've introduced in the first statement is called the inverse of T, and we'll denote this by T to the minus 1 power. Let's try to discuss a little bit of the proof of the statement. We want to show that statements I, and triple I are all equivalent, so we need to show various implications. We'll start by showing that statement 1 implies statement 2. To this end, let's first assume that there does exist a unique function u such that T compose u is the identity on W, and u compose T is the identity on V. We'll start by showing that T is 1-to-1. Let's say for the moment that T of x1 equals T of x2. Then, by using some of the algebra that you see here on your screen, we can see that x1 has to be u circle T of x1, but because T of x1 equals T of x2, we see that this is u circle T of x2. Therefore, we conclude that x1 equals x2, showing that T is indeed 1-to-1. We'll also show that T is onto. To this end, let's choose y in the codomain W. We'll denote x as u of xy. Notice that y then has to be T circle u. That's because T circle u is the identity. But this is also equal to T of x, because again we denoted x as u of y as an element of the domain V. This means the y equals T of x for some x, showing indeed that T must be onto. Hence showing that statement 2 is true. Now we'll show that statement 2 implies statement 1. So let's assume that T is both 1-to-1 and onto. We'll need to show that there exists a map U such that T compose U is the identity and U compose T is the identity. First, let's actually write down a well-defined map. Since T is onto, given a y in the codomain W, we know that there exists an x in the domain V such that y equals T of x. Since T is 1-to-1, this element x is unique. So let's define our mapping U as that sends an element y in W to this x in V. Next, we can show that this U is a left inverse for T, that is T circle U is the identity on W. Next, we can show that U is a right inverse for T, that is U circle T is the identity on V. Finally, we'll show that this map U is unique. To this effect, let's say that there are two functions u1 and u2 such that T circle u1 is equal to T circle u2 is the identity on W, and u1 circle T equals u2 circle T is the identity on V. The algebra here that you see on your screen explains why these two functions, u1 and u2, must be equal, showing therefore that our inverse u must be unique. Hence, statement 1 must be true. Finally, let's assume that V and W are finite dimensional vector spaces. Let's show that statement 2 implies statement 3. So to this end, let's assume that statement 2 is true. Since T is 1-to-1, we know that its null space is the 0 space. So this means that the nullity, the dimension of the space, is 0. On the other hand, T is onto, so the range of T has to equal the codomain W, therefore showing that the rank of T, that is the dimension of the range, is equal to the dimension of W. Finally, let's use the dimension theorem to see that the dimension of V is the nullity plus the rank, that is 0 plus the dimension of W, just equals to the dimension of W. Hence, statement 3 must be true. Conversely, we'll prove that statement 3 implies statement 2. So let's assume that the rank of T is equal to the dimension V is equal to the dimension of W. Using the dimension theorem, we now see that the nullity has to be 0. Again, remember that the dimension of V is the nullity plus the rank, but if the dimension of V equals the rank, then the nullity must be 0. Hence showing that the nullity must be the trivial vector space. So this means that T is 1 to 1. Similarly, the dimension of the range, which is the rank, has to equal to the dimension of the codomain W. But we've seen that if the dimension of a subspace is equal to the dimension of the whole space, then these two must be equal, showing that the range of T has to equal W. This means that T is onto. So we've shown now the statement 2 must be true, completing the proof of the theorem. Let's now recap what we've done and try to recall a few definitions we've just made. Again, say that we have two vector spaces V and W. The following three statements are equivalent for linear transformation T. We've just proven this theorem. Any linear transformation T satisfying either of these equivalent properties, we just said, is said to be either invertible or an isomorphism. If this is the case, we will say that V and W are isomorphic as vector spaces, and we'll use the notation V, this kind of tilde squiggle, is the same as W. This function U from part 1 of Theorem 219 is called the inverse of T, and we denote this by T to the minus 1. If T is the transformation, linear transformation, then so is its inverse. Actually, if our T here is an isomorphism, then T inverse is an isomorphism as well. This weird relation, this kind of squiggle, is actually an equivalence relation. What that means is a vector space is always isomorphic to itself. If V is isomorphic to another vector space W, then W must be isomorphic to the vector space V. Finally, if V is isomorphic to W and W is isomorphic to Z, then V is isomorphic to Z. Let's show the first statement. The idea is that we have to see how T inverse behaves on linear combinations. To this end, let's fix a linear combination of elements from our codomain W. Since T is a linear transformation, it's clear that we can write y equals T of x, where we can write x as the linear combination that you see here on your screen. By the definition of inverse, remember that T inverse of y equals x, so we do see here that T inverse preserves linear combinations. So this means that T inverse must be a linear transformation as well. Using these symmetric relations, T circle T inverse is the identity, T inverse circle T is the identity, then we can simply run through the same argument as before, as we did for Theorem 219, to see that T inverse must be an isomorphism as well. Let's focus on the second statement that we have our so-called equivalence relation. Well, the identity map is a linear transformation that is an isomorphism, so we see that a vector space V is always isomorphic to itself. Next, let's say that V is isomorphic to W. That means that there exists some isomorphism T going from V to W, but we've just seen that T inverse going from W to V is also an isomorphism. Therefore, W is isomorphic to V. Finally, let's say that V is isomorphic to W and W is isomorphic to Z. This means that there exists isomorphisms T from V to W and U from W to Z. It suffices then to show that the composition U circle T is an isomorphism from V to Z. We won't worry about showing this in detail, but we'll say that the details are provided here on the slide. This does indeed show that V is isomorphic to Z. Thanks for watching.